there is a force P there, and there are holes there somewhere here. Obviously, the cross-section of level 1 or cross-section of level 2 are different, and we are supposed to use this area because this area is this cross-section is much weaker than cross-section 1. So you are subtracting the hole for one of the rod in one of your homework, yes or no? Now, this is in the tension mode, so write it down. Now, what happened there, which I have not explained, is this. When let's assume this is the plate there, and this is the pin. So when the pin is under, when the rod is under tension, it pulls it this way. Everybody understand that? The pin tries to go that way. This is going that way. They create here a gap. Everybody, gap not is exactly like that, but for security or having a larger factor of safety, we are going to subtract the hole because there is a separation between the pin. Everybody see that? The pin and this body. Is that correct? Because the pin is trying to go that way. Is that understood? So in this scenario, you want to show the picture when the system, so let's open it like that. So it's like that. The pin comes here, so you have that, so you see the gap here. But this will not happen in compression mode. In compression mode, when you put the rod under compression, this is going to grab the pin. Everybody understand? And the pin is as strong as wood, and it is in compression. There is no separation. In tension, they are separating from each other. In compression, it grabs the pin, and pin is usually much stronger than this material. This is usually the case. So in that case, we do not need to subtract the hole. That was what your answer was different. So write it down. Subtracting the hole will be only when the rod is under tension, not compression. Compression, actually, the pin is helping resist the load. Is that understood? Yes? So that's why one of your answer for one, because one rod is under, in that homework that you were showing me, one rod is under tension, one rod is under. In the tension, you have to subtract. In the compression, you do not have to subtract. However, in some other problem, because of this, using this area and this become wasted material, and you have seen that in real life many times, why should I make it like that? Isn't that better to make the rod looks something like that? Is that understood what I'm talking about? You have seen material. Is that correct or not? So in this case, if the rod is made like that, many times you will see that. That means it is being reinforced around the hole, so the effective area is that way. So again, if the depend on the shape of the building of the rod. So if it is reinforced, what you see lots of them that happen. Look at this rod, for example. You see it right here. You see here suddenly getting a little bit larger because they don't want to use too much material because their material is wasted. You are using area of 2. Area 1 is too big. Is that correct? Why should we, again, you are making 10,000 of that or 1 million of that. Why you want to use that material? Because it goes by weight. So therefore, isn't that better to make it looks like that, as you saw in one of my handouts? Is that correct or not? Everybody see what I'm talking about, yes? And saving some material. So in that case, we are assuming this section and this section is actually the section 2 right now is stronger than section 1 even. They make it like that. So in that case, again, it doesn't matter. You should not subtract. You see some of the homework like that. You see, actually, I showed you in the handout last time too. If you see in the handout, the picture there, most of the rod are being reinforced around that area. Is that it? Now, you had another question you said? Was the same question. Okay, so I answered that question. Okay, good. Now, let me emphasize some of the points that you have to use in homework, especially the last few homework. Sometimes we give you the value of the P. I'm going to do an example like that today, of course. But let me explain it first conceptually, then I use it in an example. This is always the case. Remember that. The material is going to be covered here in conceptually. You should never remember any equation in my classes. There is no requirement of remembering the equation. The equation will be given to you. It's all about how to use it and how to apply it to different problems, as you have seen it in your homework. The more you do it, the better you get at it. If some of you are not yet have got a chance to do the homework, that means you are behind everybody else. Everybody and you are supposed to do it all during the weekend. Of course, you may have 1 or 2 or 10 different questions, everybody about different homework. That's when you come to me, or when I explain it here, you will get the idea. You just go there, finish your homework. Is that understood? Nevertheless, sometimes we give you the P. Of course, when the P is given, you can calculate the sigma. Sigma equal to force over area, etc. Force over area, which we call it sigma applied. Sigma applied, when force is given, you put it there, you have the area, that much sigma. Then I said the material, this is what we talked last time, this is repeat. The material has certain strength. If it is wood, or it is aluminum, or it is steel, at certain point, at this time, we are not talking about the detail of it, which we are going to see it this Thursday. By the way, you have a new handout that you are supposed to bring it this Thursday. Everybody should come to the class with a new handout. Otherwise, you would not understand the lecture. So everything is in those handout again. Bring it this Thursday. Nevertheless, we talk about the sigma in general there. But at this time, let's say that if I increase the load, at certain point, the sigma reaches to the highest value. At this time, we call it sigma ultimate. Remember that. So sigma ultimate. And then, of course, then you can calculate your factor of safety. The factor of safety is equal to sigma ultimate divided by sigma applied. So let's say that you have here, you calculate your sigma. It ends up to be 10,000 psi. If the sigma ultimate is 30,000 psi, you have a factor of safety of 3. You never want to load the structure to the highest value of sigma. However, one thing that I didn't mention that you probably you see it in the book, in this type of problem, since sigma equal to force over area, you have an area here, you have an area here, you can turn this into force as well, because area and area drops out. So it becomes P ultimate and divided by P applied. So sometimes they ask you how much P can be put in this material until it breaks. Everybody understands. So you have to calculate P ultimate. So this is another question. And then something else that I mentioned last time is this. This is, when I give you the force, you calculate sigma applied. Sigma ultimate depends on the type of material. That will be given a table. That table I presented to you on Thursday this week. I give you a table which shows the strength of all the different material. Is that you go to the table to find sigma ultimate. Factor of safety, again, I have to give it to you. We give it to you. You go. Sometimes we do it in reverse. I give you the sigma ultimate. This is given. This is the data. I give you the factor of safety ahead of time, and the question is, what's the value of the P? I'm going to do an example like that just in a few seconds after I go through the first two concepts. Is that understood? Yes? And that kind of problem, P is not given. This was P is given, you are calculating here. Here, P is not given. So what you do first, you calculate sigma allowable. This is sigma, how much sigma you can put on your structure. I discussed that again last time. Don't forget that. Which is sigma ultimate over the factor of safety. So let's say that the sigma ultimate again is 30,000. So you put sigma ultimate here. Let's say the factor of safety is given 3. You put it here. Then you say, okay, my sigma allowable is, this is sigma allowable numerically equal to 10,000. Then you calculate your value P based on that, because you cannot put more than 10,000 PSI on your structure. We'll see that in an example in a few minutes. So some of the problem on the first portion, which is we go forward. P is given. Sometimes P is not given. The last two problem or 2-3 problems that I gave you part of homework, you have to calculate the value of P. Is that correct or not? Now, going through the other principle, that one of the other problem is this. So write it down. The idea is the stresses along the inclined surfaces or in the slope surfaces. Let's say you have an object here. This is very, very important. In future, we are going to talk about this in detail in chapter 7. There is a chair there. You want to sit there. That's the last chair, I guess. Okay. So when we put here a tensile force of P, remember, first of all, this P has to be on the centroid of the cross section, or we are supposed to put here a rigid plate here. I did not mention that, but this is obviously mentioned that this force become uniformly distributed over the cross section. Otherwise, that will not be axially loaded member. So we are assuming P is at the centroid of the cross section. Then, if I assume X, Y, Z axis as usual like that, notice when I cut the beam in this direction, we always do that, remember, to calculate the normal stresses, this direction is perpendicular to the X. Is that correct or not? That's the vertical section that I keep showing you like that. However, let's say that this would have a grain going like that. Yes? Wouldn't you be interested to find the stresses along that grain? Yes? Because that's the weakest spot of the wood, right? So this time, this is the subject. Finding stresses on the inclined surface, or instead of having a vertical surface, this time I'm going to cut it like that, which makes an angle of theta with the vertical line. Now I want you to find out the stresses along that surface here. This is the direction. Or you can put two pieces of metal together, weld it around that direction. You just put it in the angle, weld it together, and then you are interested to find the stress. Obviously, when I cut this vertically, sigma, first of all, let's go back again to the original cut. This is the original cut. This was P. The stresses here, first of all, the stresses will look like that. That's what I showed you last time. This is the sigma. So I have a point here like that. That point, this is, we call it the state of stress. I'm going to talk about it again next week about this in detail. But for time being, there is a sigma going like that, and it is in the direction of the X. Yes or no? But if I go an epsilon to the left of it, then sigma become equal and opposite because the object is under tension, yes or no? So this is state of stress at that point. As I said, don't worry about it. All I'm saying that it's a pull that way, all the way across here. This sigma, let's call it sigma O, or in future, in chapter 7, we are going to call that sigma X. This is in reference to the future lecture. In the book, they are showing you sigma O or sigma original. Is that correct or not? So let's say that sigma O or sigma original, but future reference, I'm adding that to the system. You want to write this down, is equal to force over area. Let's assume the area of this cross section of this one. This one is, at this time, we just bypass it until I gave you. Let's say that the cross section of this wood has a cross section like this. This is the cross section of this piece of wood. Let's say this is W and this is the 8 inches, 4 inches, something like that. So therefore, sigma X equal to sigma O equal to the force. Obviously, I have to have an N here. N must be equal to P. Is that understood? Yes or no? And this become N. Is that correct or not? We discussed that. So therefore, become P divided by area, which is W times T, or we call it P divided by original area. Whatever it is. Of course, it could be some other shape. This is just for example. Now we go back to, this is vertically cut, yes or no? Or sigma in the X direction or in this direction. Now let's go to that direction and see what happens. If it goes to that direction, I have to draw still a free body diagram of the either left-hand side and the right-hand side. That's the system. However, from a static, we know this is the external force. Okay, this is the external force. What is the internal force? Internal force, obviously, N must be equal to P, but I cannot call it N anymore because that force is not normal to the surface. Everybody understand that? So therefore, I'm going to call this one F, and F is equal to P. Is that correct or not? This is the static part of it. I cannot. Is this perpendicular to the section? No. Therefore, it's not neither normal force nor shear force. Everybody understands. However, I can break it into two components. Now, what happened there? As soon as I went from vertical section to this inclined surface, The sigma is here, is there. Shear was not there. Everybody under, there is no shear stress. As soon as I go to that surface, I have a normal stress and the values are a little bit different. Let's calculate those values. That's what we are trying to do. Okay, that's very simple task. Of course, I can break this one. Remember, this angle, be careful here. I did not call this angle theta. I called this angle theta. Remember that. So if you are using my formula anytime, you should stick to this theta, or you can come up with your own equation yourself, follow the procedure. And that's the way I like it. Don't use the formula. Use your procedure. So what should I do there? F is equal to P. That's the external. That's the internal. Now I'm going to break it into two components. One perpendicular to the surface, one parallel to the surface. Now I have two forces, one normal force, one shear force. Is obvious. So all I have to do is go through the geometry. I'll leave the geometry of that to do. This line is perpendicular to that line. This line is perpendicular to that line. Therefore, if this is theta, this angle must be theta, not the other one. You should not make big mistake. So believe it from me. You can check it at home yourself. That's the geometry part of it. We are not concerned about that. That angle is theta. So what's the normal force now? The normal force N equal to what? P times cosine of theta, yes or no? Or F cosine theta, which is equal to P, correct? Which is less. But I have a shear force of P times sine, yes or no? Cosine, sine. So this is shear force of P sine theta. So I should have sigma and tau now, correct? What's the sigma is? Sigma is force over area. Okay, so now for future reference, not happen now. Now we are calculating the stresses going in this direction. But look what happened here. If this was x, this is in regard to chapter 7. Some of you may have taken this course and you know how difficult chapter 7 is, how hard it is to understand it. I don't know how many of you or which one of you, I don't care. We are starting out fresh from the beginning. But notice what happened here. As if x was here, suddenly I shifted theta degree, x prime become that, y prime become that. X and y was like that. Is that correct or not? Suddenly we are rotating it under theta degree. Theta degree could be 30 degree, 40 degree, which one of them is along that slope line and one is perpendicular. Is that correct or not? X prime is perpendicular to that inclined surface and y prime is along that surface. Is that correct or not? For future reference in chapter 7. Here they call it normal stress energy, which they call it like that. First they call it sigma theta. I would rather you call it sigma x prime, which is in the direction of x prime. Is that correct? This is again for future reference, not for this chapter. Okay, so how much is it? Force over area. How much force I have? P times cosine theta, which is less than original force, because original force was P here. Remember that? P cosine theta always less than 1. Is that correct? What about the area? Area is the same or has changed? Should I use this area or that area no longer is valid? The area has changed. Look, the area is that side. Is that correct? So what you need to do is this. To calculate this area, this is how it looks like. Correct? Yes? This angle again was theta. This I call it W. This distance I call it T. Is that correct or not? Yes? W stays the same, but T has increased. Correct? Are you with me?
I'm with you.
Good. I'm glad. I'm watching you. I told you last time. You cannot get away from me. So please, please pay attention. That's the key for become successful, not in this class as an engineer. Remember that. These two courses, not because I'm teaching, the two static and strength of material are the fundamental course. This is the one you have to really, really know in order to become engineer, everybody. So there are many different fields there, but many of them related to these two subjects. Is that understood? Therefore, you need to understand all parts of it. So this area is not W times T. This distance becomes T again over cosine theta, which is larger than T, because cosine theta is less than 1, so it becomes larger. You can again work out the geometry part of it yourself. So the vertical distance is t on that direction. That shall become t over cosine theta. Cosine theta is less than 1, obviously become larger. Is that correct or not? Yes? So therefore, my area become W times, this is W, times this distance, which is t over cosine theta. So it becomes equal to P divided by W times T. This is not dot product. This is the T multiplied. Then this cosine goes there, cosine there. There become cosine square theta. Is this stress is less than this or more than this? More? How did you come up with that conclusion, my friend? T over WT is sigma O, yes or no, or sigma X. Is that correct or not? Sigma O or sigma X times cosine square. What didn't I say? Cosine square theta is always less than 1. If cosine of theta is 0.5, square of that becomes 0.2. It's always less. Is that correct? This is very important to recognize that sigma is less than this sigma, because you are not even multiplied by cosine, you are multiplying by cosine. It's obviously, you don't pay attention to that. Obviously, the answer is obvious. I'm sure you do it. Is that correct or not? Yes? All right, so it's less than that. However, when that becomes less, what did we gain here? This is always the conservation of energy. Now this time we have a shear stress that we didn't have it there. Everybody understand that. Now what is the shear stress? So we call it tau in the direction. For time being in this chapter, they call it tau theta, sigma theta, or nu tau, nu sigma. In chapter 7, we call it sigma x prime and tau x prime. Remember that for chapter 7. This part of it, if you don't want to write it, I'm okay, but I'm explaining it when we get to chapter 7. When I make a reference to today's lecture, I hope you will remember that. So this lecture has a lot to do with concept of chapter 7 that many people fail the ME 218, they get not good a grade because they do not understand the concept of Morse circle, what was going on and what's that. So I have to explain it as we go forward. Is that understood? Yes? Hopefully it become a little bit. Again, become force over area. What force do we have this time? Shear force. Of course, this is shear force. The shear force is P sine, which is still less than P. And the area, of course, is larger than before. The area is the same area, W times T divided by cosine theta. So this time it becomes P divided by WT times sine theta cosine theta, which become equal to the same sigma O, because this is the sigma O, times sine theta cosine theta. Notice your cosine theta is less than 1, so this sigma is less than that sigma. However, here you gained a shear stress. So there is a shear stress here. There is a normal stress there. Is that understood? Yes? Now, if theta become equal to 0, look what happened, guys. Look, if theta become equal to 0, this cosine 0 is 1. This becomes sigma O. And this one, sin theta is 0. We are back to this scenario. Look, if I do that, I'm back here, theta is 0. So I have this sigma, no shear. Everybody understand? Remember that, because in Thursday I'm going to give you the general state of stress. You will see at each direction there is a sigma and there is a tau. This I will explain. It is been explained in chapter 1, but I usually leave it for a little bit further until you get a little bit understanding of all the concept of stresses before we get there. But remember, on each surface now, at that surface, if I'm looking at this direction, I want you to understand, if I'm looking at this little piece of this direction, so I look at that. Right now we have a sigma, nu sigma, which is equal to sigma O cosine square theta. Everybody see that? And there is a shear force here, which is tau equal to, I just calculate that, sigma O times sine theta cosine theta. We talk about this on Thursday or next week about how this is happening. Is that understood that? So therefore, write it down in your note. The state of stress at any point, the state of stress at any point depends on the direction of the cut or direction of the surface we are looking at. The state of stress at any point depends on the direction of the section or the direction of the cut. And the stresses changes according to the angle that we choose. One of them is the highest value. 1 sigma is the highest value, and 1 tau is the highest value as well. Can you tell me in this problem what is the highest value of sigma? When cosine theta become equal to 1, that theta equal to 0. That's the highest value. So this sigma was highest value. Tau was the lowest value. Is that correct? Equal to 0. As soon as we have there, obviously, if, as I said, this is always less than 1. So sigma has reduced, tau has increased. Very important phenomenon that. So in other words, stress at any point on a structure is like hydrostatic pressure. I want you to, and you don't have to write this one. Just I want you to imagine this. When you put some object under the water, you know that from physics, the pressure coming from all sides. Is that correct or not? All of them are equal. When you are looking at an object there in any structure you have, and you look at any point of it, stress is coming at all the direction as well, but it's not hydrostatic pressure. They are not the same. In one certain direction, it is the highest value. We discussed that in chapter 7. Don't worry about it. This is preview of coming attraction. So you have this wall, you press it there, you can see the crack start at certain angle. You never see, I mean, you see sometimes crack vertically too, but usually the cracks are not vertical, yes or no? Where do you think that crack is? Where the stresses are the highest value, whether the shear stress or the normal. This becomes a phenomenon related to chapter 7. I'm just mentioning for you, you have heard it, you want to forget about it for time being, this is okay. But for time being, all you have to do, calculate your normal forces and shear forces divided by area. You get your new normal stress. That's all they are going to ask you at this stage. You want to use my formula? Remember that. You have to use this theta, not this one. Sometimes purposely they give you this angle. They call it theta. That's not the one I use. Remember, if I use that, sine become cosine, cosine become theta. So if you are using my equation, you should remember which is the theta, which is not. So don't just jump. If I do not suggest use this equation, I suggest you use your own process. Cut your section, find your new section. It's just a little math. Is that correct? Find your forces. Forces divided by area. Okay. So this is one concept that I didn't mention that I have given you 1 or 2 homework. Everybody recognizes that. I don't know how you did it, but this is the concept behind it, which is very important for future. Now, next example I want to do, go to page 12. Remember, we did problem number, the middle problem. I don't know what problem number was, but let's look at another type of connection there. And this connection is a wood connection I want you to look at. I'm going to put it on the board anyway. So it is on page 12 of your handout. We did middle problem last time. Remember that? Calculating internal force versus external, which is the subject of one of your homework or 2 of your homework as well. Now let's look at this connection. And this is the type of work that you need to practice in order to become good at. And the more you do your homework yourself, not through the solution manual, the better you get at it. So remember that. This is already, I'm giving you some hint how to process this example. Generally, I should not give you that. Everybody understands, just because this is your first exposure. So here what we have. So this is another type of connection, which is not the pin connection. Remember, last time we talked about the pin connection and how those work. So this time we are talking about sometimes this happens in the wood structure. So I'm going to show that here we have one material here, which is the T-shaped rod. So I'm going to look at it like that, which is connected to another material like this. So we put here like that. In order for you to see what's happening here, I'm going to make this in 2 different, perhaps color or shade. As you see it in the handout, they made this a little bit darker. Notice this material or this piece is different of the white one. Everybody see that? This become a connection, correct? Yes? Cut and groove or whatever you want to call it. Now, when I put here this part of it under a tension force of P equal to 6 kilonewton, I believe it's 6 kilonewton, yes. And I pull this one, correct? The idea is what's going to happen here, what part of this structure or this material going to damage, or what you are supposed to do. But by the way, many things happening here. Some of them are being asked, some of them are not being asked. So you have to be careful when you read your question. There could be 10 different things happening there, but you just answer the part that's being asked. In this problem, they are only talking about the shear stresses. So not about the normal stresses, etc., or bearing stresses. First of all, what do you think happen if I don't tell you anything, but just looking at the picture, you are pulling it, what do you think going to happen? Are these two materials touching each other? Yes. Which area? I mark that again. If I pull it that way, is that correct or not? Do you have a bearing stress there? You are pushing against it. That's not being asked. However, it's there. Is that correct or not? Yes? This piece of the rod will be under tension. That's not being asked. This is just to show you the two questions that we are asking is the punching shear. Is this material going to be punched? Notice I just even give you a hint. I show you the punching area. But you don't have to look in your homework or your quizzes. You don't have that luxury. You have to decide. This is your first exposure, so I show you an example or two. Then you do your homework. Then you are ready for the quiz. Is that understood? Yes.
In a question where it mentions average shear stress, is that?
That means it is on this total area. All the shear area for time being is average because we are assuming uniformly distributed over the entire area. In other words, this is what we said last time too. If you have an area like this, you put glue here and you put it here, that area all being glue, we are assuming the shear is average. However, that could be not the case. Maybe in the corner is less than. Inside, we are going to talk about it again in chapter 6, how this is going to happen. There are changes or not. For time being, we are talking about sigma average and tau average, uniformly, good question, uniformly distributed over the entire area. That's right. If there is any variation, we talk about that. We have to wait until week 9. Yeah, week 9. Is that correct? Go to chapter 6. Is that understood? Yes? Is there shearing here? Yes. Yeah, look, if I pull this one, first of all, the first thing you should do, you should always come up with the static part of it. Static means separating these two materials from each other and drawing the free body diagram. This is very important. If you don't do that, you don't see much. Everybody understands that. So by doing that, or in any of your homework, so if I draw that piece again, one more time, and I put this time the dimension there. Look at this is piece 1. Is that correct or not? You are going to put here 6 kilonewton. Where is the touching point? The touching point is the maroon area. Yes or no? So at that time, I should have a force there. Yes? But they are symmetrical, top and bottom. So each one will get 3. So which way should I put it here? So obviously here is the touching point. Is that correct or not? Here was the area, correct? So here I have 3 kilonewton and 3 kilonewton. Notice this is static. We have talked about the static a lot. Material 1 pushes toward the blue material. Yes or no? Material blue pushes back on the white one, material 1. Is that correct? That's what I'm showing that. Everybody see that? So everybody should be clear about action and reaction. That is the free body diagram on that piece. Yes or no? You are pulling it this way. The other material tries to push this way. Is that correct? Which causes, this is what I show you, which causes a shearing off there. Is that correct or not? That shearing off is a surface, as you said it, average shear. Is that correct or not? Yes? What is that area if you go three-dimensionally? I show this lower piece, and that lower piece looks something like that. Everybody see what I'm talking about? Is that correct or not? This length, given how much? You see, this is our dimension curve. You have it all there. I have it here. So that length is given to you. That length is 100 millimeter or 0.1 meter. Is that correct or not? Yes? There, correct? So this piece, this length, here, 0.1 meter, which is this length from here to here. What's the depth or the other dimension of that? Is that given to the depth? We are not showing that because this is three-dimensional object. It's going like that. Is that correct? It says in the text of the problem. The depth is 100. Read it. You need this. You need to read the question. Otherwise, this doesn't mean anything. The depth of the beam or the object is 150. In other words, if this is 100, let's put it this way. If this is 100 millimeter, this is 150 millimeter. So this area being shear off. Where is the force is here. This is the 3 kilonewton. So you must have a shear force of, just being complete, you have a shear force of 3 kilonewton here, which we can assume uniformly distributed over the entire area. That's what you were asking, correct or not? Yes? Okay, so tau equal to what, guys? Tau equal to force. What is the, first of all, it is double shear. Everybody understands. So I have to get half of the load, one area, or two area, and total load. Everybody see, this is the idea that I presented to you last time about double shear or single. But you don't have to look at both of them. You look at one side of it is correct. It's 3 kilonewton and one area. Is that correct or not? So how much is the tau? Tau is force over area. The force was how much? 3. So 3 times 10 to the power of 3 Newton divided by area. Our area is actually 0.1 meter multiplied 0.15 meter. So meter square, which ends up into Pascal. Newton over meter. Please always use Pascal, not Newton meter square. We know Pascal is Newton over meter. The same, PSI is pound per inch square. So therefore, the answer tau become equal to 200 times 10 to the power of 3 Pascal. And since this is wood, we call it equal to 200 kilopascal. So the average shear stress on the level AA. Everybody see that? Yes? Do you see the picture there, level AA? Yes? But there are two of them. They're only showing one of them. Is that correct? As I said, this is an exercise, class exercise. I'm showing that. If I don't show that, you have to pick it up yourself in your homework and quizzes. Is that understood? Yes? Okay. Is there another way of damaging this structure? Yes. You see, that's line BB. In other words, if this is the whole idea, if this is not thick enough, you see, 100 millimeter is about 4 inches. Yes or no? So if you're making a piece of wood in 1 inch into 2, it easily is going to shear off. Everybody understand what I'm saying? That here I use 4 inches as 0.1. So if this is 1/4 of that, the stress becomes 4 times more. Is that understood? So easily you damage it going through that. This is one bad idea that we are removing. The other one, this could be small. Everybody understand? Because this instead of, I don't know how much is that. That's 125 millimeter. Or it is about 5 inches, because 2.54 millimeter, everybody knows that. It's a 25.4 millimeter is 1 inch. Is that correct? So it's approximately about 5 inches. So if you make this too thin, then what's going to happen? This is, let's assume this is metal. This will cut through that. Is that correct? So the other possibility, there is one possibility we already checked that. That was AA. That was AA. Is that the other possibility is, look at it, where is going to cut? That one. This is problem your number 18 in your handout. I hope you have done problem number 18 without reference to your solution. Hypnosis, I'm being very honest with you. I hope you are honest with yourself. If for that problem you went to the solution manual, you look there and say, oh, I understand this, you ruin the whole homework for yourself. That's not what I'm asking you to do. Going to the solution manual and understanding the solution there is like lecturing. You need this to practice. The more you practice, the better you get at that. That idea has to come to you independently from any outside source. Of course, you need help from me, which is office hours. You need occasionally, I hope you never go to the solution manual, but you go to the solution manual to check your answer. You don't go there to find a process. If you're looking at the process, something, I'll tell you this again and again. People come to me at the end of class, they have done it in a static, they come in there, I did all the homework, I got 100, but I'm doing very badly in the quiz. I said, okay, how many times did you go to the solution manual? How many times did you come to me, or how many times did you go, your friend ask for the solution? If you are doing this, keep doing this. You are not learning it. Some people, other people learning it and telling you what to do. Correct? You're going from point A to B, a new address. If I tell you turn right, go half a mile, go turn left, go to another, you don't remember anything. You just follow me. Is that correct or not? Until you do it independently 2-3 times, you recognize everything. Yes, you recognize I have to go there, I have to go. This is the process. The process is for you guys to keep practicing this. That is the solution to that becoming successful here. Anyhow. So what is now the next tau that we want to calculate? That was tau in level AA. That was level AA. Now I want to calculate the tau in level BB, which is the cut in blue material. Yes or no? But what's the thickness of that one now? That one, the thickness of that one is 1.25. Again, the depth is the same, so I'm looking at this one or that one. I have to look underneath it. Again, this time is a piece of material. This is not. This is solid. It's like that. And here is 125, and here is 150. Is that correct? So that area being shear off. So this time, tau is equal to tau for level BB. So that one was tau for level AA. According to the picture I gave you. And here tau BB become equal to, again, force. The force is the same thing. Remember, I have to show you that. Because when now if I show you the blue free body diagram of the blue part, so you see this, again, I have to be, so now you have 3 kilonewton here, 3 kilonewton there. Everybody see what that, and they have 6 kilonewton there. This is the free body diagram of the blue piece. That's the free body diagram of the one piece. Of course, you can guess that yourself. The forces, 3 kilonewton forces must be equal and opposite. And therefore, that's why you have a shear failure here and the shear that very touching each other. Shear failure there. So the tau become, again, 3 times 10 to the power of 3 Newton. The area this time, this distance from here to here is 0.125. So 0.125 times the depth is the same depth, 150. Obviously, this is a little bit less because we have larger area. So the tau BB become equal to this time 160 kilopascal. Now, is there any other point of this structure to be checked? Yes, but it's not being asked. So in your homework, do the same thing. If I have talked about 10 different subjects, what they are giving you as a data, just follow that. That's what I'm saying. So there could be, in a structure, there could be 10 or 20 or 100 different things can go wrong. Just stick to the part that they are asking. In this part, all they are asking is for shear. That's what we did. Of course, everybody recognizes there is a bearing here between the two material. There is a normal force in this rod, etc., etc. Is that correct or not? Yes? That's not being asked. Okay? All right. Now let's go to, is there any question in reference to all your homework? Notice by doing this, you have a couple of homework like that. There is a rod is being, for example, if you have a rod here like that, and you are pulling it that way, there is a possibility of shear failure here, everybody. And that I'm doing this in order for you to do your homework. There are a couple of homework like that. Everything that I do in a class here, one way or another, in different format, appears on your homework. You are supposed to recognize that. Is that correct? If somebody else, again, repeat, if somebody else does it for you, that's no good. That's all I'm saying. That. Okay, now let's go to one of the quiz problem, because that puts everything together. Go to the last page of your handout.
We are almost done with this handout. That's why on Thursday we need a new handout, new subject. So go to one of these problems. Let's look at problem number 2, for example. Look at problem number 2. There is a bolt there. That could be a quiz. It is part of your home. You have one homework like that. So you have a bolt and there is a washer there. The washer has a bearing, I showed you last time. Yes or no? The pin is under tension. There is the possibility of shear failure. Yes or no? Punching shear, which is problem number 18 in your homework, correct? So all of that. Now let's do problem number 1, which I'm concerned. I want you to, because a couple of homework is like this as well. The P is not given. We are going to this system. We are trying to calculate the value of the P. Most of your homework, P is given. Few homework at the end you have which P is not given, and I'm concerned about that. I'm sure that some of you already have done it, but let's do one of this together, and all together, all of it. So let's go to problem, first quiz in page 12. All right. So this is the structure. You have here a rigid beam for time being. This one we consider rigid because we cannot handle that. Remember, so far we are talking about normal forces and shear forces in a two-force member type structure. Is that correct or not? We are not talking about bending or torsion, etc. Here, this rod is being pin connected to the wall like that, and there is a force P. Generally, P always will be given, but in this problem, P is not given. First of all, is this a complete structure or not? Yes or no, and why? Is this a complete, if I have a rod like that, pin connected to the wall, and I put a P there, is this a good structure? Will it stay there? Will not stay there? Absolutely not. That's correct. This is a very bad. So it's not going to stay there. If that. Why? Because it is. I want you to understand. Because it is a pin connected. You have a rod here. You put here a pin there. You hold here. You put it with a pin. This is a structure. Is that correct? It just cannot stay there. I have to put something underneath it or hold it with a rope or something. Other words, if this was a fix, that would have been a different story. Everybody understands. In the fix, this is a complete structure, completely. I can load it here like a balcony type, sort of. You start in the balcony and stay there. This you cannot do. Is that correct? Yes? So what they have done here, look at the picture. They have put another rod on top of that to hold it up. Is that correct or not? So that rod, this is understanding of the nature of the problem. So from there, we go on. This is, again, pin. Sorry for that. So this is pin, again, to the wall at the same time. And the way it's given, this is 8 inch, this is 6 inch. So the slope of that is 3 run and 4 rise. And I believe this is A. They call this one A, this point B, this point C, this point D. And BC is 6 inches and CD is 3.6 inches given to you. The more detail comes as we go forward. I ask you to look at the more detail of it. But the point is this. If I give you the P, you should be able to calculate all the forces as I did it in example 1. Remember example 1 I did from the handout? Remember there was a rod there, there was a rod underneath it. Remember the first example I did? That should not. But here P is not given. However, you should process this exactly the same format. So in other words, you should draw free body diagram of BCD. Is that understood? Yes? All right. As soon as you draw the free body diagram of BCD, let's see what we have there. Free body diagram means separate this everything from it. So I'm going to put the P there, whether it's given or not, that's immaterial. However, let's discuss that here. B is a pin, yes or no? So when I take it out, I should put there BX and BY, okay. At C, I have a disconnection too. I should usually put there CX and CY. Of course, that's not the case. If I do that, I have 4 unknowns, so it becomes 1 too many. Of course, AAC is a 2-force. Remember the force going in the direction. We just did that in the first. So here, when you disconnect that, you see here, I call it FAC or CA or whatever. That's correct, because it starts from C going to there, I call it CA, which is the same as FAC in magnet. Yes? All right. Now, when people saw that for the first time, if they recognizing this idea here, they say, oh, how many unknown do I have here? 1, 2, 3, and 4. So oh, this is not solvable. So, however, you should not mix the P with the black one with the color one. Is that understood? If P was given, you could have solved that one. Yes or no? By taking moment about point B, like we did it in the earlier problem. So what I'm saying that when you get into this type of a structure, you should everything is a backward. The sigma allowable is given, and you want to calculate the value of the P. Assume P is given, proceed. That's what you have to do in all these problems, which is the engineering problem, because many times you design something and you want to see how much load you can put in it. Is that correct or not? So there is two ways of doing it. I give you the P, you calculate the stresses. Or I make the structure, I ask you how much load can I put in this structure in order the stresses not to exceed certain limit. What are the stresses? What are the stresses given here? Let's understand that. You see exactly like there, but I'm going to erase down this thing because this one type is this, P is given, you calculate. These are the earlier problems. The later homework are like that. Is that correct or not? What's the maximum sigma that your ultimate is given? What is given? Read the question, tell me the number. This is what you have to do about every homework. To do it yourself. I can put it here, I know that. Sigma, my ultimate is given how much? 50? Yes, very good. So let me put it here. These are the data. Sigma ultimate in any part of this structure not to exceed 50 KSI, which is 50,000 PSI, yes? How about the shear value? The shear value is tau ultimate again, is not to exceed 25 KSI, for example. Is that correct or not? Yes, this is just an example. If it's true or not, we'll discuss that later on. Comes Thursday again. And then do we need a factor of safety? Because this is ultimate. At this number, it's going to break. What's the factor of safety we need? 2.5. So whatever load I have or whatever stress, I want 1/5 of that. Is that correct or not? Yes? Okay, how do we proceed there? Assuming P is given, you calculate all the unknown in terms of P, as if P was given. Is that correct or not? Yep. All right, what will be the value now? Can I take the moment about, again, remember, this is 3.6. This is your free body diagram. This is 6-inch, and this is 3 run and 4 rise. Can I take the moment about point B? Yep. Yes. So in other words, I'm saying that proceed the problem exactly as if P is given. So don't forget about the P. Just P is given. P was 1,000 pounds. You would go ahead. Yes or no? Let's assume P is given. As you see, I did not include P and this reaction, not in the same format. I make this black, this one. All you have to do the same process. Sigma M at B equal to 0. So you get what? You get P times what? P times 9.6. Negative or positive? Negative plus, I take the word down. Now you break this, of course, to two components. We have done that. Remember, class 1, example 1 I did in class was this way, is that when I was calculating the internal forces. Exactly the same problem. So you have a horizontal component which doesn't have a moment. You have a vertical component which is 4/5 of F. That's right, 4/5 of FCA. But we put that in one parenthesis because I have seen lots of mistakes like that. When people see force and a number, they think this is force, this is distance, they forget about the number. I have seen many mistakes like that. This is still force, is that correct? What's the distance? The distance is 6. Many people forget about putting 6 there because they see 2 numbers there. So please avoid that mistake. This is the force, the distance still is 6 inches, yes or no? 4/5 of the force, which is the vertical force, multiplied by that distance, which is 6 inches, is the moment, and the moment is positive. So that one becomes equal to 0. And there, or 450, yeah, that's 450. So therefore, when you calculate the FCA becomes equal to 2p. So this is the static part of it. No matter what you put here 1 pound, this becomes 2 pounds. You put here 1,000 pounds, this becomes 2,000. This is the relationship, which is the geometry. It is nothing, you can change that. Is that correct or not? Then you calculate Bx and By. Okay, so this is again a static part. Everything in terms of, you will see lots of problems like that in a strength of material, which you did not see it in a static. In a static, always load were given. Here you are designer. Remember that? You want to make something. You want to see how much load you can put there before it fails. That's the question. Yes, so what is the Bx there? Bx is equal to, after you use sigma fx, so let me give you the number. That is very simple. So, okay, I have to just, you can calculate your own, by the way. So Bx become equal to 1.2 p. So whatever value p is, that become 1.2. The direction is correct because it came positive. And By, when I use sigma Fy, it become minus 0.6 p, which is negative, means that direction is incorrect. That is a static problem. Everything was in terms of p. Now I have to check to see which part of this structure, which you already have done it in first few homework. If you have done your homework, of course, you have already done that. What should I check? Of course, I cannot check member BCD. I said you cannot do that because that's not a two-force member. Your two-force member is AD. AD is under tension or compression? You're not answering me? Is under tension, or when you pull this object out, is it under tension or compression? What do you think FCD is? FCD is going away from the joint C. That means that member CD is under tension. You're quiet, huh? Come on, guys. You remember that the trusses, forces? You know what that FCD is? The FCD, that means that rod CD is pulling this member up. Is that correct? Or like a cable? Yes? What's the cable under then? First FC, is it tension or compression? Guys, something that I don't want to repeat here. I thought you are very good at that one. Sorry to say that. This is the cut here, yes or no? The rod is sitting still there. Everybody understand that. You draw here a force going away from the joint. That indicates that rod is under force equal and you are showing the free body diagram of the joint. You discussed that in a static. You all got A and B in a static, aren't you? Yes, so you should remember that one. So the rod is under tension of FCD. That's the whole thing. We did it in chapter, the other part 2. Is that correct or not? Yes? Mm-hmm. So what should I, so that member is going to be under normal stress, yes or no? Normal stress, the force is FCD. So therefore, now here is the analysis. That I thought is easy to understood. When you put this force here, means that member is under tension of FCA, which is 2P. Is that correct or not? Yes? So, okay, what is sigma equal to? This is the idea. Sigma equal to force over, this is sigma is normal stress. Force over the what area? Now let's look the area. Because I just go step by step in order for you to understand. I didn't want to give you all the data. I need the cross section of this rod, which is under tension. Is that correct? That cross section could be like this. It could be hollow. It could be solid. It could be square. It could be rectangular. What they have given you, this distance is 1/2 inch, and the thickness. In other words, this has a cross section like this. I want you to understand it. 1/4 inch by 1/2 if I cut it. Is that correct or not? Yes. Or like this. Don't forget about it. This is, yes? 1/2 inch is sitting like that. Is that correct or not? Yes? 1/2 inch by 1/4 inch. Is that understood? Yes? So sigma equal to force over area. You see, this sigma equal to force over area is going to appear in every lecture, but in different format. What force, what area, that's your decision. Is that correct? Formula is very simple. Okay, what force do I have? What's the force? FCA. What is FCA equal to? Because I'm looking for P, so I don't put FCA. I put here 2P. Is that correct or not? Yes? That's what, if you see sigma equal to P over A, that P is symbolic. Is that correct? I said the amount of normal force. This is the normal force. Divided by area. The area is 1.5 inch by 4 inch. Really? Is it there is a hole there? Is it a pin there at the beginning, at the end of that rod? That's what I was talking at the beginning, guys. Is this like that, or is it being reinforced? It doesn't say anything. The picture doesn't show anything. So I have to subtract it. It is under the tension, but this cross-section and this cross-section is much weaker than this cross-section. That's what we had before. So I have to subtract here the whole, because it is not in the compression mode. Somebody asked me. It is in, you were asking me, yes or no? It is in tension mode, then I have to subtract. Is that correct? Or unless it's built like that. If I build like that, the picture will show it, or I will tell you. Is that correct or not? Yes? Mm-hmm. So nothing is given. So the area actually is like before. The area is not. This is the area in general. This is 1/4 of an inch. This is 1/2 inch. Is that correct or not? But now I have to subtract the whole. Is that correct or not? So the resisting area is remain. So I need look at read it. I need the diameter of the pin A or C. What's the diameter of the pin? I know that. I want you to be able to read this quickly. And the diameter is 5/16. So the area that remained there, the 1/4 of an inch remained the 1/4 of an inch. That you cannot change it. So I put it in this format. Then here become 1/2 of an inch minus the diameter, which is 5/16. That's right. Minus 5/16. So that's the area. So because I have to subtract the whole, again, I made a reference to that at the beginning because it is under tension. Now, here P is unknown. Of course, sigma is known. But sigma, I have to use the value ultimate. Yes or no? The value ultimate is 50K. So therefore, this cannot be more than 50 times 10 to the power of 3 pound per inch square, or PSI. You usually put PSI, but since the first time I want you to, this has to be in pound, this has to be in inches square. This is the first few times you do it. Of course, the only unknown is P, correct? You calculate the value of the P. The value of the P ends up to be equal to, that's 1,172 pounds. So if I put 1,172 pounds here, this item reaches to 50 KSI in tension, which breaks. Is that because that's the ultimate? Is that correct or not? So it's no good. So if I want to have the right answer, I have to divide that by a factor of safety of, but we don't do that until we check every other part. Remember, a structure has 10 different parts, 100,000 parts. You don't send a shuttle to space. Remember the first shuttle, you were not born at that time. Actually, I was there when it happened. The first shuttle, I always tell the student, I was there, actually standing there. The first shuttle with that multi-million-dollar project, I don't know, 500 million or what, it broke because a $50 O-ring didn't work because the cold weather, I'm sure you have read about it. It was a cold weather, it was icy, so it was, we talk about the temperature effect on the structure later on. Structure changes the dimension, stresses. Anyhow, it could not, it was supposed to protect any leak, the gas leak, and then it was explosion. So a $50 damage could have been changed if they had time or knew ahead of time. It would not save the whole structure. That's what I'm saying, that you have a road road, you have the flat tire, might as well you take your bike in the places. So therefore, a structure breaks in the weakest spot. Is that correct or not? What are the other points that I have to check? This is the whole point here. Is that the whole point of the story was check everything. What other points do I have to check? Pins. The pins here, this pin, and this pin is going to be like that again. Yes or no? Correct? Yes? On there? shear stress, yes or no? Correct? So write it down. This was normal stress, if you want to specify that. This was normal stress in rod. I checked that one. Then now I'm talking, because the data that's given, notice that only tau. There is no bearing given. There is no ultimate given, etc., etc. I mean, the ultimate is given. There is no bearing given, that nothing else given. So I'm checking that one. So pin A and C. Now, both of them, the load force on the both of them is FAC. Is that correct or not? 2P. However, are they the same size, or there are different size, different type of thing? Read the question. Again, I know the answer. The answer is there are 5/16 of diameter, and they are both the same. Is that correct? So I don't have to check both of them. I need to check either of them. Is that correct or not? So tau, so write it down. Tau at A, which is the same as tau at C. See, these are pin. Equal to the force. Force still is, because that's the same rod. Look at it. This is FAC or CA. This is FCA, and this is the pin, and the pin is going to shear off, as we discussed it. Is that correct or not? What the same force, so the force is 2P. Is that correct or not? Yep. Divided by area of the pin. Area of the pin, we know that. It's pi times radius to the power of 4. Yes, the diameter was 5/16. The radius becomes 5/32, half of that. Is that correct or not? Or you can use the pi/4 diameter if you want. But this is, I use because this is, 5/32 to the power of 2. But this should not now exceed how much? Exceed 25 KSI. That's right, because 25. So there we put here 25 times 10 to the power of 3 PSI, or pound per second. You calculate the value of the P. The value of the P this time become 950. This was a quiz, by the way, in the past. 959 pound. 959 pound. Now, if I have these two numbers, which one is the governing? 959, because at 959, pin is going to break before the rod. That is the structural analysis, we call it. Is that correct or not? So if you have 10 different points to check, you have to check every point and use the weakest part of it system. Is that correct or not? Or the largest area? Yes.
So like if you had different materials, say rod BCD was wood and this was AC was metal, you'd want to check the wood.
Of course, yeah. Every part of it, there are many other things that I haven't even mentioned yet. They are shearing there, but as I said, check the one that's been asked. We are limited you to 2 or 3. Yes, all of it has to be checked. Yes, of course, yes. Everything has to be checked, correct. Okay, what else did I ask you to check now? The next one, which is our concern because it happened in your homework, I asked you also to check the pin B. Okay, this people make mistake there. Of course, pin B is under force 2. What force? That's the question. These are all static base, but you have not seen it, so I have to mention it once or twice before you get into your homework, but this happened in your homework as well. This was very simple. This was a 2-rod member. It was a rod like that. Everybody see that? Under a purely tension of 2P. Is that understood? Yes? What's happening at B? What's the force at B? Is it BX? BY? Or both? Both. Yes. All right. B equal to, I'll show you now how that works. B equal to BX squared plus BY squared, which is square root of 0.6 P squared plus 1.2 P squared. So it becomes equal to 1.34 P. Now, what happened here that you don't see or you want to see, of course, this is a static. Look, when you put here under a tension here, when you pull it here, guys, everybody, when you pull it here, look at this. When it touches here, your force is P. Is that correct or not? So you have a P like that, which when you cut it here, it becomes a shear force. Yes or no? Here you have a force like that and a force like that. So obviously the shear going to be in on the under the resultant of these two forces, because this is round, so you have a force here 5, you have a force here 4, so obviously the answer is here. Is that understood? That's what I'm doing that. Because the shear off is at the resultant of these two forces is going to shear off like that. Is that understood? Yes? Look, it is like that. The pin is sitting like that, but it's the force here, a force here, so you have to find the resultant. So that's what we are doing. The resultant force acting on this pin is 1.34 P. Should I check it, or is it the same size or different size? Read the question. Is it the same size as the other two pin, or because when I did as a homework, some people stopped there and said I don't need to check it, and they are right, because the force is how much force? 3.4 P. Yes. If I want to calculate the tau here, so this shows you how you are involved with the problem. Here, notice I checked it for 2P this area. First of all, this is not a single shear. That is a double shear. So I have to divide the load by 2. Okay, 1.34 P by 2. Of course, if I was using a different size pin, as one of you mentioned it, or somebody there, I don't know, somebody was mentioning it, you have to check that. But this is the same size pin, isn't it? Here I had 2P. Here I have 0.67P. Do I need to check it again? The area is the same. The load is much less. Is it going to be effective, guys? No, you are not becoming engineer yet. I cannot call you junior engineer. Not yet, guys. Maybe at the middle of the course somewhere there I call you junior engineer. Not yet. You have not done it yet. You have not at least showing me yet. I have the same area, less load. Do I need to check it again, or already check it for 2P? This is less P. This is math. Yes or no? Now you want to do it, go ahead, do it. But why do you want to do the denominator is the same. It's got the same size pin. So 532. Don't you see that this load is much less than that one, and this load, obviously, this must give me a larger P. Is that correct? No? Okay. That should not be more than or equal to everything else is the same except this load versus that load. Yes or no? Anyhow, you calculate the P. I don't even want to put that. That becomes 2,800 something. So as I said, many people decided that that is not needed to be checked. Everybody understands that. It's less load, larger area, the stress becomes so there. P becomes 2,862 pound, as it is very safe. Actually, if anything, I should have make this a single shear and the other one in the double shear to be a better design. Hold on one second. And therefore, still we have not the final answer. Now, which one is the governing factor? Which one is going to be weakest link in this, as we call it? Weakest link is the pin A or C. What's the value P allowable now I want to put there? So you throw this out. You throw, of course, that one out. You take this one, and your P allowable become equal to this 959. You don't have to do all of them at the same time. Notice one thing else too. Factor of safety does not apply to the cross section. Factor of safety only applies to the sigma and to the force. I mean, if the area become twice, not necessarily factor of safety become twice. Everybody will have to, you have to be careful about that one. So we only apply that. Anyhow, 2.5, I'll discuss that again later. And therefore, safely you can put in this structure 384 pounds of force here in order this, and the cross section here all to be safe. You had it.